So we're on the brink of creating these absolutely massive AI swarms, right? But we're hitting a wall, a big one. We keep trying to be the perfect puppet master, pulling every single string for thousands of little robots. But what if that's completely the wrong way to think about it? What if the secret to building a real hive mind isn't about control at all, but about building them a whole new, better universe to live in?
I mean, just think about it for a second. 1,000 drones painting a masterpiece in the sky, each one a perfect brushstroke. Or hey, 1,000,000 nanobots swarming inside your body, hunting down rogue cells with flawless precision. This isn't just sci-fi anymore, this is the next frontier. But getting them all to work together, to act as one, well, that's one of the biggest challenges in AI today. And it's not just a problem of scale, it's a problem with the very foundation of how we're building them. Okay, so here's the classic approach versus the one that's inspiring all this new research. On one side, you've got the central brain model. One big server calling all the shots. It's a single point of failure, a massive bottleneck. But then you look at nature, a flock of birds, a school of fish. There's no CEO bird up front telling everyone to bank left. The global order just emerges from super simple local rules. And that decentralized genius is exactly what we're trying to tap into. To really get why this new approach is such a breakthrough, we have to understand just how deep the problem with central control really goes. It's not just about lag or the server crashing. No, it's a fundamental issue of space. And, believe it or not, time itself.
So, the first core problem has this kind of technical name, the geometric capacity bottleneck. Sounds complicated, but the idea is actually pretty intuitive. The flat, grid-like digital worlds we build for our AIs just don't match the crazy, branching, tree-like shape of complex information.
Right. Imagine taking a huge family tree or any kind of branching hierarchy and trying to squash it flat onto a single piece of paper. You just can't do it without crushing things. Branches get smushed together, distant relatives suddenly look like neighbors, and the whole structure gets distorted. At scale, this causes catastrophic information loss for an AI.
The second problem is even weirder, almost philosophical. It's called the temporal binding problem. Okay, so you have 1,000 agents, all working on different little pieces of a big puzzle. How do they synchronize? How do they know they're all part of the same moment, the same single thought, without a central conductor yelling, 1, 2, 3, go? And this is where the research completely flips the script. What if we've been trying to solve the puzzle in the wrong playground this whole time? The answer isn't a more clever algorithm or faster processor. It's a completely different kind of space for the AI to exist in, a different geometry. So, on the left, you've got our familiar, flat Euclidean space, the world we know and love, where area grows polynomially. But on the right, we have hyperbolic space. The best way to picture it is like a saddle shape, constantly curving away from itself in every direction. And because of that, its volume grows exponentially. This means it has practically infinite room for those branching, tree-like structures to grow without ever being squashed. And the paper puts it perfectly. This new geometry isn't just a mathematical party trick. It's a practical solution. It allows for massive parallel growth where agents can organize themselves without ever running out of room or bumping into each other. It just completely removes that geometric bottleneck. Okay, so we solved this space problem, we built a new universe, awesome. But what about the time problem? How do all these agents, now living in this huge, weird, curvy cosmos, actually sync up and work together? Well, the answer, beautifully, comes straight from physics. It all comes down to something called the Kuramoto model. It's this really elegant piece of math that describes how things that have a natural rhythm, think fireflies blinking in a forest or neurons firing in your brain, will just start to sync up all on their own. They do it just by sensing their immediate neighbors. There's no conductor, no central clock. It's global order emerging from local influence. Now in this new framework called Hyperbolic Neural Cellular Automata, or H-NCA, they put this principle directly into practice. Each little agent is an oscillator. It has a phase, a point in its own cycle. And by simply trying to match its phase with the neighbors it can see, the entire swarm starts to find a shared pulse. That's it. That's how you solve the temporal binding problem, not from the top down, but from the bottom up. So how do we know this really works? Well, we can measure it with something called the Kuramoto order parameter, or just R. When R is close to 0, you've got total chaos. Every agent is just doing its own thing, on its own rhythm. This is what it looks like at the very beginning. But just watch what happens. After only 25 steps, with agents just talking to their local buddies, you can see that R value starting to climb. Pockets of coherence are forming all over the place. You can literally see the swarm starting to find its beat. And by time step 50, that order parameter has jumped up significantly. A global rhythm has emerged from purely local rules, just like the model predicted. The swarm now has a shared heartbeat, a collective sense of time. It's amazing.
Okay, so we've got a space that doesn't create bottlenecks and a mechanism for getting everyone in sync. So let's look at how this all comes together into a real, functioning, self-organizing system. The process for each individual agent is this simple, elegant little loop. Step 1, perceive. It just gathers info from its immediate neighbors. Step 2, process. It runs that info through its own tiny neural network. And step 3, update. It changes its own state and its own phase based on that decision. That's it. It's an incredibly simple set of rules, but when you repeat it thousands of times in this special hyperbolic universe, you get truly intelligent, coordinated behavior. And when you put the two systems side by side, well, it's not even a fair fight. Centralized systems scale terribly and are super fragile. This H-NCA system scales exponentially. It's incredibly robust because there's no single point of failure. And it's wildly efficient because all the communication is local, no lag. So what does this all add up to? It means we can build systems that are literally self-healing. If a chunk of the swarm goes down, the rest just reorganizes around the damage. It means systems that are incredibly fast with zero server latency. And systems that can scale to mind-boggling numbers without breaking a sweat. They hold together in space and in time, creating something that, well, it starts to look a lot like a true intelligent collective. And this is way bigger than just a cool way to organize some virtual drones. This research points to a fundamentally new way of thinking about and building artificial intelligence itself.
The paper makes this absolutely fascinating suggestion. Because of its unique geometry, this kind of system might be the perfect petri dish for the most complex type of behavior we know of, something called Class 4 dynamics. This is the sweet spot, right on the edge of order and chaos, where things like life and universal computation are thought to exist. The complexity isn't programmed in, it just emerges from the physics of the system itself.
The potential here is just staggering. We could use this to model incredibly complex biological systems, like how a brain actually wires itself up. We could build knowledge graphs that can finally scale to contain all of human knowledge, or create generative AI that can design complex hierarchical things from the ground up. It's a whole new foundation for any system that needs to organize itself. So I'll just leave you with this question. We've always kind of assumed that intelligence needs a center, right? A command hub, a brain. But this research suggests that might just be a limitation of our own thinking. What if true, massive-scale intelligence can emerge from the bottom up, born from a few simple rules playing out in just the right kind of universe?